Welcome back to Alex Support Help with your host, Mr. Walker. Now, going back into this, we are now in Geometry Unit 1. This video I'll just have as a solo video in general, simply because I don't feel like splitting it up like I've been doing. Because some of these videos will be short, some of these videos will be long, and Goal 1 tends to be very intertwined. I will have links to different topics in this video, so you don't have to watch through the entire video to get to the topic you need. But other than that, let's go ahead and get right into this. Talking about midpoint of a number line segment, integers. All midpoint means is the exact middle point between your 2 points on a number line. Think about median from goal 6 of algebra 1, where you had to find the middle number in your set of numbers. So there is multiple ways to find your midpoint. I'm going to give you the one way that will work no matter what, whether or not you have a number line, whether or not you have a graph. As long as you know the points, this will work. So we are going to use our values of -9. Oops, let me do this. I'm trying a new drawing software for these videos. So -9, and we have -5. To find the midpoint, we are going to find the absolute value difference of these two values. So if you remember, absolute value just means the distance from 0. So basically speaking, whatever this is, we're going to make it positive. So the -9 minus -5 becomes plus. So that's -9 plus 5, which is -4. And remember, absolute value makes whatever that is positive. So the distance between P and R is 4. And we can check. From P, it's 0, 1, 2, 3, 4. So yes, that's confirmed. To find the midpoint, you find the absolute value distance, or distance in general, between your 2 points. Divide that by 2. So half of 4 is 2. And you either, from your leftmost point, add 2, or from your rightmost point, subtract 2. And that's it. So what is -5 minus 2? Well, 1, 2. What do you know? We have a -7. So if I'm going to throw that in there. And there we go. That's how you would take care of your midpoint line segments. Remember, this is the way that will help you a lot with the future topics as well. Sure, you can easily just count it out, but this is going to really help you if you understand this now with your future topics. So let us go ahead and move on. And as you'll notice, I actually have finished the first 2 of this topic, so I could just move straight ahead. Segment addition and midpoints. In the figure below, N is between M and O. O is between N and P. If MP is 16 and NP is 13 and NO is 7, find MO. So I'm going to actually zoom this in so that we can work a little bit easier, because I don't actually, you know what? I'm gonna redraw this. So let me get my drawing tool out, this interesting color. So I'm gonna just make my weird line. Actually, let me do this. Skadoop. Way cleaner. All right. So on my line, I am gonna have. Oops, I'm still learning this drawing software. Is it this one? I'm going to have M, N, O, P. So we are told that MP from M to P. Our entire line is 16. We are told that NP, this part down here, is 13. So already going off of this, if the entire line is 16 and most of this is 13, we can automatically deduce that this small part over here is just 16 minus 13, which is 3. Why? Because 3 plus 13 equals 16. That's one part figured out. We still need MO, which will be this part and this part combined. So moving on, we know that NP is 13 and NO is 7. Well, we can actually stop right here because MO is just MN plus NO. We found out what MN is, which is 3. NO was given to us, which is 7. And 7 plus 3 will give us that answer of 10. Now, the only thing to really watch out for in this is that sometimes what will happen is you are given, I'm just going to make this up really quickly. Oh no, I keep doing this. You are given just M, N, O, P. They might say something along the lines of N is midpoint, ... right? All that means is that the left side of what it is and the right side is equal. So if N is the midpoint of N and O, that means that the distance between M and N is going to be the same as N and O. So if they gave us this and they said, oh, by the way, MP is 16 and NP is 13, using our same math, we would say, oh, that means that MN is 3, but we automatically know, I'm just ignoring this, we automatically know what MNO is because it has to be the same as MN. So this would be 3, this would be 3, and by convention, 13 minus 3 is 10. And so in these cases, when they say that something is the midpoint, they'll only probably give you one part of it, or you have to find one part of it because they want you to understand that both sides of your midpoint are equal at all times. And that's it for a problem like this. Identifying transformations. For problems like this, they will give you 3 different vocabulary you need to understand, even though they'll give you 4 vocabulary in your picture. So let's start off, and I'm just going to shorthand this because I'm still learning this drawing software and don't want to make the most horrible writing mistakes. Actually, I can just do this. Let me just open up my text box. All right, so you have translations. A translation is literally just moving your figure. Think of it like moving your phone. If you move it straight enough, it's going to be in the same exact position, the same exact way. Everything about it is the same. It's just in a new place. It's like if you stood up from your chair, moved to a different chair, and sat down. You're still the same exact person, still facing the front of the room. You're just in a new place. So for example, this is a translation. This arrow is still facing the same way. It's the same size. It's facing the same orientation. It's just moved. So this is a translation. Next up, what we have is called a reflection. So a reflection is a flip, just plain and simply. Your shape isn't turned, it's flipped. None of these are reflections. However, if I were to draw this arrow and this arrow, it's kind of hard. They're close enough to reflections. They're on the same imaginary line. They're just flipped. Yes, it's not perfect, but generally think of yourself in the mirror. Everything about you should be the same. The only difference is that it's backwards. It's flipped. That's it. So none of these are a reflection. Your third type of vocabulary that they give you is what we call a rotation. Think about, going back to your phone analogy, you just turning your phone on the desk. It might be in the same position, but it's just facing a different way. So this right here is a rotation. It's the same exact shape, it's just turned. So again, these might seem simple so far, but they're very crucial in understanding geometry. So yeah, basically a translation is moved, a reflection is flipped, a rotation is turned. And the last one they give you, this is also a rotation by the way, and they don't tell you what it is on this because they don't want you to know just yet. This is turned. The last one they give you is a, let me write it down here actually. A dilation. A dilation is a shrink or grow. So this one is a dilation. It's the same shape. Sure, it's in a different position, but they're not the same size. It obviously got bigger. So it's not any of the ones they gave us, but that's called a dilation. Translation, reflection, and rotation are what we call rigid motions. Nothing changes about your shape outside of its position. A dilation is a non-rigid motion, which means that your shape can stretch and shrink and all the extra fun things. So basically for these, if it turns, it's a rotation. If it flips, it's a reflection. If it moves, it's a translation. And that's it. Finding distances between points that share a common coordinate. So there is something in geometry called the distance formula. We will not get into it in this particular topic because it's not needed whatsoever. But I will briefly talk about it in a future topic. For this one, common coordinate means that your x's are the same or your y's are the same. If that is the case, to find your distance, you're just finding the difference between your non-same values. So in this case, my y's are the same, so I'm actually just going to ignore them. Let me do it that way. No, that's a highlighter. Let me do it this way. So I'm actually just gonna ignore my y's. So I'm gonna do the same thing I've been doing. The absolute value distance between 4 and -6, which is 4 plus 6, which is 10. Oops, that is a 16. That is supposed to be a 10. I do not know how to erase yet. So I would just put down my answer as 10. So distance for this particular topic is simply find your value, either x or y, that are not the same, and just find the distance between them, which is the absolute value, the first value minus the second value. And that's it. Translating a point and giving its coordinates, one step. We're now going to be translating, and if you remember from a couple topics ago, translation simply means you're moving. If you notice, you got this giant finger here, which allows you to move your shape to where you need it to go. So, in this case, the figure below has a point marked with a large dot. What is that point? Well, that's just 5, 3, which will go here in my point of the original figure. They want me to translate or move this unit 6 units down. What that means is I'm not going to go any units left. I'm not going any units right. I'm just strictly dragging it straight down. And I can use this big blue point as a means of making sure that I don't move. So I'm just going to go down 1, 2, 3, 4, 5, 6. And that's it, because it's only one step. So what's the point in my final figure? That is going to be at 5, -3. And that's it for this type. Naming angles, sides of angles, and vertices. Here's where things get tricky if you don't understand your shapes, your angles, or if you just skip the ALEKs explanations at the beginning all over. So, to be very brief, an angle is formed by two rays that share an endpoint. So for example, if I draw this and then I draw this, that is an angle. Two different rays, which in this case, let me get all fancy with it. I'm going to attempt, because I'm bad at this, to call this A and B and C. They both share point C, which we're going to call a vertex. And AC is one ray. CA is one ray, CB is my other ray. And those are the sides of my angle. So the sides of your angle, let me put it, sides equals a ray. So I'm going out of order with this, where it says name the sides of angle 1, as the ALEKs explanation will go into as I just did. There will be rays, and rays are denoted with the ray on the top of it. How do you name a ray? Always, always, always start from the vertex, or the point that the rays converge at. In my case, that is CA and CB. For angle 1, which is just this angle up here, I'm going to actually cross out this stuff down here. Get my draw out. I'm going to cross out this part down here because we don't care about that. So angle 1 is all of this up here. So what are the rays, or my sides? FG and FE. Again, always, always, always start from the vertex. That is how a ray is named. And what is the vertex of H? Well, I gotta bring that back now. Get my eraser out. Oh, that's a tiny eraser. Let me do it this way. What is the vertex of HFG? HFG? Well, that's just gonna be F. There's no special symbol denoting a point, and F is a point. One cheat code for vertices is that if they give you the angle, it will forever and always be the middle letter in that angle, assuming it's a 3-letter angle. So in this case, HFG, it's going to be F because that's the point that's between it all. And what are the other names of EFH? So in this case, we're going to be ignoring, let me pour that over here. We're gonna be ignoring, oh, that's my eraser still. Oh, I'm learning. This. So, an EFH, what are the names? Angles are pretty easy. They're named forwards and backwards, as well as by the interior degree. So for example, and just as a cheat code for this particular topic, angles with names will always be angled. EFH is one way to name it. What's the backwards way? Well, it's just HFE. And what's the inside angle name? Well, that's just angle 2. Those will always, in these examples, be the 3 names for your angles. The number that's on the inside is by itself, or the forwards or backwards way to name it. Those are how you name angles. Just remember that names for angles will have the angle symbol, sides for an angle will have a ray symbol, and your vertex is just the point, and a problem like this should be easy to grasp. Reflecting a point across an axis. A reflection just means you're flipping it, just like in a mirror. You're in the same position, you're just being flipped. So, our first part about this, using the pencil, plot the reflection of point A across the y-axis, is asking yourself, what is the y-axis? Well, an axis is either going to be the vertical or horizontal line of our coordinate plane, and if you forget what it is, it makes it easy because the vertical line is what has our y on it. So this vertical line is our mirror, as I'll call it for reflections. So we're not going to go up or down. Why not? Because then we're going to be in a different position from our mirror. We're going to count the number of spaces we are away from our axis. So I am 1, 2, 3, 4, 5 spaces away. So I'm just going to count another 5 spaces on the other side of our mirror. 1, 2, 3, 4, 5. Plot my point, and boom, my point A has been reflected. Now, if they ask us to reflect over the x-axis, I would do the same thing with my horizontal line. It would just be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Notice how if I am reflecting across the x-axis, I am only going up or down. I am not going left or right. And if I'm reflecting across the y-axis, I am only going left or right. I am not going up or down. Think about your image in a regular mirror, not a funhouse mirror, not a broken mirror, just your basic bathroom mirror. You're not in some weird position. You're just where you are on the other side of this mirror. You're not further up, you're not further down, you're not diagonal, you're just directly across from yourself. So if you just understand which axis means which direction, problems like this should be pretty simple for you. Finding side lengths of rectangles given one dimension and an area or perimeter. I'm not going to go into what area and perimeter is conceptually, because even if you have forgotten, ALEKs can do that for you. I'm going to cut straight to the point. For problems like these, let's start with area. We should already know that at least for a rectangle, area equals length times width. In this case, we're given our area of 7,154 meters squared. We're finding our length, and our width is 73. So to solve that problem, if we just divide both sides by 73, we should be able to get our length. So 7,154 divided by 73 is 98. Straight and simple. Now, let's go to perimeter. There is many ways to write perimeter. I'm going to write the basic way as well as a mathematical way. By mathematical, I just mean simplified way. So perimeter for any shape is just adding together all the sides. For a rectangle, as you should know, there are 4 sides. There is the length. Oops, I keep doing rectangles. There is the length, which is the same on the other side, and the width. So perimeter would naturally just be length plus width plus length plus width. Because we're dealing with variables here, we can actually simplify this. I have 2 lengths and 2 widths. In this case, we know our perimeter is 336. We're looking for our width, but we know our length is 91. Now I know that 2 times 91 is 182. So we have our linear equation. Subtract 182 from both sides. And then we would just divide that final answer by 2. So to just do that in one fell swoop, we are going to do 336 minus 182 and then divide that by 2 and get a width of 77. Now here's a cool little math trick you probably learned back in one of the goals in Algebra 1, where it came to rewriting equations with just letters. Area and this problems are pretty easy. Perimeter, you can actually do this in a very short way. Since we know that perimeter is 2 times length plus 2 times width, and we'll be looking for one of these values, if I solve for length, I'd get perimeter minus 2 width equals 2 length. And if I divide by 2, I'd get that half of the perimeter minus the given width equals my length. So if I put 336, I'm going to use the exact formula. So if I did half my perimeter minus the given length, because width and length be interchanged in this formula, I'd still get 77. So that's, if you ever wondered why do we ever need to learn those things in Algebra 1, they're useful for the next math at the barest of minimums. But other than that, that's it for a topic like this. U.S. customary length conversions with whole number values. Now, I'm going to be forward about this. Geometry Goal 1 has a lot of these. So you're going to have length conversion values, you're going to have volume conversion values, weight conversion values, and I think that's roughly it. They're all the same thing. The concept between area conversion, they're all going to be roughly the same thing. So at least for the first three, which is going to be length, volume, and weight, I'm just going to do it in this one video. There is simply one concept to pay attention to in all of these types. Using my unit table, if I'm going down, so say from inches to yards, I am going to be dividing whatever units I have. If I'm going up, so let's just say from yards to inches, I'm going to be multiplying. What by? Well, that's where these fancy little conversions are going to come into. So 3 yards to blank feet. Yards to foot is going up, so I know I'm multiplying. By what? Well, there's 3 feet in 1 yard. So guess what I'm multiplying by? That's right, 3. So that'll just be 9 yards. 9 feet. Same exact thing, or concept I should say, when it comes to inches. I have 84 inches and I'm going to feet. I'm going downwards, so I'm dividing. By what? There are 12 inches and 1 foot, so I'll just divide this by 12. And that's 12, 24, 36, 48, 60, 72, 84. That is a fancy 7. So that is 7 feet. Like I said, I'm just going to go ahead and right into the next one because it's all the same thing. We are going to go straight into weight conversions. Side note, if you're wondering why I already have 2 of these done, I did that off camera because I don't feel like doing it later. So, same exact thing. Down division, up multiplication. Ounces to yards, ounces to pounds. 80 ounces going downwards, that's going to be division. What am I dividing by? That's sweet 16. 80 divided by 16, that is 16, 32. 32 plus 32 is 64. 64 plus 16 is 80. So that is a 5. So that would be 5 pounds. And last we have pounds to tons. That is 16,000 pounds. Going down to tons, that's another division. Dividing by what? Fancy 2,000. Little cheat code for dividing by numbers as large as this. When you're dividing, you could just start crossing out zeros. That's what I do. 16 divided by 2, that is 8. Just 8 tons, period. All right, one more to go, because I think the area one might be slightly different. All right, quarts to pints. We are going from quarts to pints. We're going up our table. That is multiplication. Multiply by what? There are 2 pints in a quart. So 3 quarts, 6 pints. And I'm not going to write this next one down. We're going from cups to pints. So it would be 18 divided by the 2 cups it is to make a pint. So we get 9 pints. In all honesty, these are things that if you cook, if you make things, you have probably done before. I cook a lot, so I do have to do some conversions here and there in my recipes if I'm upscaling or downscaling, so that's useful for me. I have some friends who are in carpentry, and they always have to convert, especially when dealing with large pieces of wood. And so that's a thing as well. And I have a couple of medical friends who deal with weight conversions. Not on that scale, mind you, but still deal with weight conversions. And that will be it for this 3-in-1 topic. Reflecting a point across an axis and giving its coordinates. The figure below has a point marked with a large dot. First reflect the figure across the x-axis, then give the coordinates of the marked point in the original figure, and then the final figure. I'm a little rule breaker, so I'm going to do my coordinates first. The point in the original figure is 2, -6. Look at me breaking all the rules. As I mentioned before, when we were reflecting a single point as opposed to an entire shape, reflecting across the x-axis is only moving up and down. Reflecting across the y-axis is only moving left and right. Actually, in this case, you don't have to move anything. You're going to be using these 2 functions. This one reflects across wherever you put this line at. So if I put it here, boom, got reflected across the line. If I put it down here, it's off the graph because it's too far. So we know our y-axis is right here, up and down. So if it was asking for me to reflect across the y-axis, I would put this line down, which we call the line of reflection, because in mathematics we're so original, and boom. That's how my shape would look if it was reflected across the y-axis. But that's not what they're asking. They're asking for the x-axis. So if I put that down here, that is the reflection of my point across the x-axis. And using the same tactics I did in the single point example, I can just double check. I'm only going to check 1 point because I'm lazy. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, everything's going to check out here. So in my original figure, my point was at 2, -6. In my final figure, my point is at 2, +6. And that's it for a problem like this. Identifying linear pairs and vertical angles. I'm not going to spend time defining vertical angles, linear pairs, and supplementary in the mathematical terms because they're blue highlighted terms. You can just press on them for the explanations. No need to be that lazy. I'm going to give 2 little bits of information that you need to know for these particular examples. So let me actually buff that up a little bit. Boom, right here. Vertical angles are the same as congruent angles. Linear pairs are the same as supplementary angles. And that's important to understand here. As you may or may not remember, vertical angles means in terms of 2 lines, when the lines make an X, they're just directly diagonal. So 2 and 4, 3 and 1, 6 and 8, 7 and 5. So vertical angles, I'm just going to give 5 and 7. Linear pair, right next to each other, either horizontally or vertically. So to be a rebel, I'm going to give 3 and 4. Supplementary angles is just linear pairs. So I can either re-give 3 and 4 like a scrub, or I'm going to give 6 and 7 because I want to be fancy. And so long as you just remember this and you read up on the definitions for vertical and linear pairs, problems like these are very simple. Determining if figures are related by rigid motions. In each part, use the tools to move the solid triangle exactly onto the dotted dashed triangle. If it is not possible, click on Not Possible. As you may remember from the translation, rotation, reflection, none of the above topic, a rigid motion has your shape transported to a different location. It's going to be the same size, just a transported shape. This is our translation, which is just going to move it but keep it in the same orientation. This is our rotation, which keeps it in place but turns it around. This is a horizontal reflection, and this is our vertical reflection. And that's Not Possible screen. So basically with this topic, there's no real cheat code. You just kind of try your best to get your shape onto the dashed shape. And if you tried everything you possibly can and your shape is either too big or too small, then it's not possible. Otherwise, if the shapes are the same size, it will be possible. So for example, that one I thought was not possible, but I just had to rotate it a tiny bit more and it fit like a glove, assuming the glove is your size. And that's it for this topic. Solving equations involving vertical angles and linear pairs. For those of you who missed the math, well, it's back. I'm going to just write this up here because we're going to need it for any and every of these problems. Vertical angles are equal and linear pairs equal 180. To solve these type of problems, you just have to make up formulas. So I have 7x plus 53. I'm gonna call this a actually. Yeah. Wait, no. Let me pop that. There we go. I'm gonna call you A. I'm gonna call you B, and I'm gonna call you C. I see that A and B are linear pairs. That means that A plus B equals 180. A and C are vertical angles, so A equals C. And I know that B and C are also linear pairs. Now I have two different variables, x and z. So if I started with this one, 7x plus 53 equals z. I'm stuck. I have an x, I have a z, I don't know what either one is, I can't do anything with it, so I'm going to save that for later. The same thing goes for b and c. So I'm actually not even going to use this because I don't have to. I'm going to start with a plus b equals 180. Why? Because they both have x. So 7x plus 53 plus 9x plus 31 equals 180. 7x plus 9x is 16x. 53 plus 31 is 84. Subtract 84 on both sides, and I get 16x equals 96. Divide by 16, and I'm going to say that's 7. No, not 8. This 6. It has to be 6. Is 16? Is that 6? 16 times 2 is 32. 32 plus 32 times 2 is 64. 64 plus 32 is 96. Wow, that's 6. So x equals 6. Now that I know what my x equals, let me just plop that down right in here. I can now solve my problem over here. That is 7 times 6 plus 53 equals z. 7 times 6 is 42. 42 plus 53 is 96. So my x is 6 and my z is 96, assuming my math checks out because I didn't use a calculator. Aww, my math didn't check out. Well, time to pull out that fancy calculator. 7 times 6, 42 plus 53, 95. Aww. And that's the beauty of ALEKs. Sometimes you get too cocky and you get burned for it. Well, I can just show a quick little example now that I messed up everything. I'm going to just do this very quickly because the point is given. What has the same variable? Well, b and c. And what are b and c? They're linear pairs. So 7x plus 27 plus 11x minus 9 equals 180. 7 and 11 is 18. 27 minus 9 is positive 18. Subtract 18 on both sides, and we get 18x equals 162, and divide by 18, and x equals 9. How do I know that? Because 18 times 10 is 180, minus 18 is 162. So my x is 9. I got a linear pair going. 11x minus 9 equals z. So 11x minus 9 equals z. I'm going to cheat here real quick. Are you ready? I know it's going to be 11 times 9. And multiplication is just repeated addition. So I have 9 added to itself 11 times. If I take away one of those 9s, that's just 9 times 10, which is 90. And I'm going to live and die by that answer. You can check my math for yourself, but as you can see, when you understand how to manipulate numbers, you can save yourself the calculator. And that's it for a topic like this. Translating a point and giving its coordinates. 2 steps. Uh-oh, we're back to these graphs. And we're not just doing 1 step. We're doing 2 steps. It's the same thing as the last translating a point, so I'm not going to even go into explaining this. I'm going to just go right into breaking rules, and my original point is 5, 7. I am going 7 units to the left. 1, 2, 3, 4, 5, 6, 7, and 4 units down. 1, 2, 3, 4. And my point on the figure is now -2, 3. And that's it. One way that I actually do these, because I just am a math guy, is I don't even count the spaces really. I just do the math. 7 units to the left is just subtract 7 from your x. 5 minus 7 is -2. 4 units down means subtract 4 from your y. 7 minus 4 is 3. So even if you're not given a shape and they tell you about these translations, you're just doing addition and subtraction. And that's it for a problem like this. Conversions involving measurements in feet and inches. Now, this is a topic I've recently gone over with the class because I do an after-school class with carpentry kids, and this is the crux of carpentry. You're not going to walk into Home Depot and say, "Hey, can you give me a 97-inch piece of wood?" Because they'll laugh at you. And how do I know? Because I did that, and they laughed at me. It was actually kind of funny. We're going to convert from inches to feet. Now, one thing you're just going to have to know, if you've never seen a ruler in your life, is 12 inches is 1 foot. And if you remembered from the other conversion problems, when you're going from a smaller unit to a bigger unit, you're dividing. So we're dividing 97 by 12, but not so fast. Whatever we get, the, what is it called? There's quotient, there's dividend, divisors. The quotient is going to be our feet, whereas the remainder is going to be our inches. You see that grayed out calculator? You're going to want to do long division. Why? Because if you, actually, let's do it this way. Ready? We are going to pull out a calculator, and we get 8.083 repeated. Okay? Let's put that as best as we can into ALEKs. 8.083 repeated. Exactly. So you're going to actually have to do long division. And sure, why can't I just use ... Well, because that's cheating, and we're not basic around here. We actually do our math. Basic stuff is for the scrubs. So let's go ahead straight into this. Long division isn't extremely difficult, and if you want to make it easier, just write down your 12's timetable. We have 12, 24, 36, 48, 60, 72, 84, 96, 108, 120, 132, 144, so on and so forth. Each one of these represents a foot, because these are my inches. So 1 foot, 2 feet, 3 feet, 4 feet, 5 feet, 6 feet, 7 feet, 8 feet, 9 feet, 10 feet, 11 feet, 12 feet. Dr. Seuss books. So we just pretty much say, hey, it's a price, and it's really just the price and right. The price is right. You're trying to find the closest number without going over. Is it 12, 24? Nope. 96 is the closest I can get without going over. So that's 8 feet. Just like our calculator answer. How many inches? Well, you would just subtract the 8 feet. Oops, 90. Oh, that's what the 8 feet, which is the same thing as 96 inches, and you're just left with 1. So now you see that just rushing to a calculator isn't going to get you these type of problems. You're going to have to actually do the math. The same thing goes here. 63. 1, 2, 3, 4, 5. 5 feet. 63 minus 60 is 3. So if you're not comfortable with long division, and what that would look like is this. Let me get my little drawing tool. We'd have 12, 63. 12 goes into 63. 5 times minus 60 is 3. So that's 5 feet and a remainder of 3 inches. That's the same exact thing as writing out your 12's timetable and just kind of going from there. So either way you do it, this is how you solve these problems. And this is a very easy way to solve it, so that if you ever get a job and you have to do this, you're not looking silly reaching for your calculator all the time. And that's about it for this type of problem. Was I mistaken? I think I was mistaken. So we have 6 feet 3 inches tall, and we're converting strictly to inches. So we have 6 feet 3 inches. If you didn't know, the 1 dash is feet, the quotation marks is inches. So our 3 inches, we can kind of just put off to the side. 3 inches. And we're going to convert our feet to inches and then just add that back to our 3 inches. So if there are 12 inches and 1 foot, and we're just converting that out, remember, if you're going from small to big, you divide. And if you're going from big to small, you multiply. So you would just do 6 times 12, and you would get 6 times 2 is 12. Carry the 1. 6 times 1 is that, plus that. 72. There we go. 72 inches. And 72 plus 3 is 75. If you kept your 12 timetable down, you can do the same thing. You would just be like, oh, 1, 2, 3, 4, 5. Oh, that's the 6 feet. So you would just toss your 72 up there, add it back to your 3 inches, and go from there. So again, either way, this type of problem shouldn't give you too much of a trouble if you understand how to convert from feet to inches. And that's about it. Translating a polygon. This has no cheat codes. It's just memory match, connect the dots, coloring book stuff. If you remember, translation just means you're moving your shape. What that technically means is you're moving each and every individual point of a shape the same amount of units. So, to translate a polygon, we're going to find our 4 major points, or our major points in general, no matter how many it is, 4, 18, 2, 3, etc. This shape has 1, 2, 3, 4 vertices. Again, vertices are just the endpoints of angles, or basically where your lines bend. So we're just going to move each and every one of these vertices. 2 units to the left and 1 unit down. So starting here, I go 1, 2, 1. Here is 1, 2, 1. 1, 2, 1. 1, 2, 1. And here's the hard part, is connecting the dots in the right order. Because if for some reason you skip over some dots, you'll end up getting a weird looking shape. My recommendation is to kind of just go straight to the line tool and do 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, and then connect that last one. Whatever makes you feel more comfortable, so long as you connect your dots in the right order, problems like these should not be a problem for you at all. Finding the coordinates of a point reflected across an axis. Notice how they're no longer babysitting us with shapes. We're doing straight math, y'all. This is a very simple concept once you get it down. In a mirror, if you raise your left hand, it looks like your reflection is raising its right hand. If you raise your right hand, it looks as if your reflection is raising its left hand. Basically, the opposite is happening in a mirror. The same thing applies for reflections across the X and the Y axis. Basically speaking, if you're reflecting across the Y-axis, your Y stays the same and your X is negated, which means you're multiplying it by -1. A negative times a negative is a positive. If you're reflecting across the X-axis, your X stays the same and you're flipping your Y. Basically, whatever axis you're reflecting across, keep that variable the same and flip the other. Let me actually write this out. So reflect across x-axis for the point xy. Reflect across x-axis is going to be keep the x, negate the y, and your reflects across y-axis is going to be flip the x, keep the y. That does not mean your y has to be a negative number. That means whatever your y is, multiply it by a -1. Just like in this case, it was already negative, so it became positive. Other than that, that's it for this type of problem. Measuring length to the nearest quarter or half inch. Now, for those of you not familiar with how to use rulers, this is going to be a difficult one for you, but I'm going to try my best. First things first, this is your ruler. Greetings. you're going to align the 0 of your ruler with the first dotted line, always. What I suggest doing is actually dragging it down so that the shaded part is not touching your ruler, only because the distance between these two dotted lines will be the same no matter what, and it's easier to see now. The only way I can really describe this is keep in mind that you have to count the number of points between your whole number. So between 1 inch and 2 inches is 1, 2, 3, 4, 5, 6, 7, 8. There's a total of, oops, that's not it. There's a total of 8 units between every single inch. And what's half of 8? 4 is our 1/2 point. So if I count in 1, 2, 3, 4, this is our half. Since it's also talking about quarters, what's 8 divided by 4? That's 2. So every 2, so this is 1 quarter, this is 2 quarters, this is 3 quarters, is going to be our quarter marks. And so you're just basically seeing which one is it closest to. In this case, we're looking at a 1/2 inch. So our half would be 1, 2, 3, 4 in, and we're seeing which one is it closer to, 1/2 or 0, because 1/2 inches go from 0 to 1/2 to 1. Your quarter is 0, 1 quarter, 1/2, 3 quarters, and 1. So is this closer to 5, 6, or 1/2? Well, I hope it's obvious here. This is closest to 1/2. So what is our 1/2 inch answer? 5, because you start with the number of inches, and, oops, 1/2 inches. Let me actually zoom out. There we go. And that's it for problems like these. Metric distance conversion with decimal values. I'm going to try to truncate this because you should have read the ALEKs explanation to really understand how this works. But here we go. We have millimeters, centimeters, decimeters, meters, and all the way over here is kilometers. I put that over there for a reason. So 10 millimeters equals 1 centimeter. 10 centimeters equals 1 decimeter. 10 decimeters equals 1 meter. And that's what we'll stop for right there. I'm actually going to also move meters. 1,000 meters equals 1 kilometer. And I actually don't need that right now. And that's the table of metric numbers. With that math, if I'm going from millimeters to decimeters, that would be 10. That would be, remember, if I'm going down, it's division. So millimeters to decimeters, I would take my millimeters, divide it by 10 to get centimeters, divide it by another 10 to get decimeters. So I would divide by 100 or divide by 1,000 to get meters, and so on and so forth. So if I'm going from millimeters to meters, I'm going to take, let me change colors, my 19.8 and divide it by 10 to get centimeters, divide it by another 10 to get decimeters, and then divide it by 10 to get meters. Or altogether, I would just take my 19.8 and divide it by 1, 2, 3 zeros, 1,000. That might seem like a daunting task, but if you remember how to multiply and divide by powers of 10, you know that that's just going to be moving your decimal point. So right now, my decimal point is here. And since I'm dividing, I'm going to move it to the left. How many spaces? The number of zeros. So I have 1, 2, 3 zeros. So I'm going to move it 1, 2, 3 spaces and add in a ghost 0 for good measure. So the answer to this would be 0.0198 meters. And you'd get the same thing if you put it into that. All Alex is telling me is that typically numbers aren't just point, they actually start with 0, but I was lazy. And that's it for a topic like this. Analyzing relationships between points, lines, and planes given a figure. Now here's where we're going to have to think outside of the box. If you did not look at Alex's explanation, shame on you, because this is going to be a wild ride, and I'm going to go through this fast. Co means same. So collinear is just same line. Coplanar is same plane. So when they ask us for J blank and blank are 3 distinct points that are collinear, distinct just means different. So we're looking for 3 points that are on the same line as point J. So we have J, K, L. And when they ask for M blank, blank, and blank are distinct points that are coplanar, my plane is this paper, as I call it, Z. And so I'm going to find the 3 additional points that are on my paper, which luckily for me, there are only 4. H, M, N, and K. So I have M, I'm going to put in N, K, and H. Please, please, please note, Z is not a point. It is a plane. So Z would never end up as one of our answers. Now that we're done with that, let's go ahead and get to the somewhat obvious, somewhat not obvious thing. If I draw, oops, that's not drawing anything. If I draw, there we go. Stop. If I draw this line and this line, A, B, A, C, these 2 lines are intersecting. Even though they start at a point and it's an angle, they're still intersecting. That will come in to play in an example you might get later. And those examples are typically, imagine a line is drawn from H to L. Which line intersects HL? Well, you would just find a line already existing that shares a point. H doesn't have another line coming out of it, so L does. So in this case, the line LK or LJ would be intersecting. And that's for some of the examples. For this particular example, it is less hard. It's just looking for intersecting lines. Which line intersects with NK? Well, JL does, or JK, or KL. The point is, you can name a line with any 2 points on the line. So either JK, JL, or KL. A plane is named by any 4 points on our plane. The only thing is that all 4 points cannot be on the same line. That means there has to be at least 1 point that's a rogue point. So I got a line, M, K, sorry, so let's back it up. A plane is named for every 3 points, not all collinear. What that means is that I can name a plane with any 2 points on one line and 1 extra point left over. So for example, what are 2 points that are on a line on my plane? Well, M and N. And what's a leftover point not on that line? Well, H. Or my 2 line points could be M and K or N and K. The point being, my plane cannot be named M and K. That is just the line. I need 1 rogue point to define my plane, so H will do. And notice how it has to be on my plane. J and L are not on my plane. This is where the ALEKs explanation would come in handy, but if you could understand the definition of coplanar, how to define a plane, etc., a problem like this won't be too difficult. Matching basic geometric terms with their definitions. This, in my opinion, is the best topic to start off with, but obviously that's too late. And I say that because if you understand the definitions for everything in geometry, it makes solving equations so much easier. I'm not going to answer these per se. Actually, I will. I'm a liar. But I'm going to actually give you the definition for every single thing on that list as best I can. So, we have perpendicular lines. There's way more to it than what I'm going to say. I'm going to give the easy boy definition. A perpendicular lines are two lines that cross and they form a, where's my pen at? Right here. And they just form right angles. Those are perpendicular lines. They're not any lines that cross. No. They're special lines that cross. They're lines that cross and form right angles, which means that on a perpendicular line, each and every angle formed by it is 90. That's a perpendicular line. Parallel lines are two lines that just basically never touch. In geometry, we say they're in a plane, basically, and again, on a piece of paper. So imagine this computer screen is my piece of paper. On this computer screen, these two lines should never touch. And so they're parallel. What else we got? We also have coplanar. We talked about this in the last topic. Coplanar just means on the same plane. Again, just using my bad analogy, piece of paper. This is my piece of paper. All of this stuff is on my screen. You can't see it, but my notes for videos is on my other screen. And so that's not on the same plane. Collinear means on the same line. So in essence, this term and this definition are collinear. They're in the same line, kind of. Line segment is just this. So if this is a line, I'm just going to make this up. This is going to be a very poorly drawn one. This is a line. It has two arrows. A line segment is just a piece. So it starts and ends at a point. That's a line segment. An angle, we talked about this. It's just two rays. Again, this is a ray. It's just two rays that shares an endpoint, or as we call it, a vertice. And I think there's only one more. Oh, circle. A circle, now it seems simple, but in geometry it's very specific. A circle is all points that are equidistant from a central point. What that means is if I measure the distance but from this point to here or to here or to there or to there or to any part of my circle, they would all give me back the same length. You'll learn about that in a future topic, and that's called radius. But basically, to make it easy, the most complex definition up here will be circle. The set of all points in a plane that lie the same distance from a single point in the plane. That's a circle. Otherwise, it's an oval. And lastly, we have congruent. Ready? The hardest one up here. Congruent is same. Same size, same shape, just same. So, using our definitions, The first one, circle. Intersecting lines that form a right angle, perpendicular. Same is congruent. And a figure formed by two rays having the same endpoint is just an angle. And so geometry, unlike algebra or like algebra, it's very, very definition heavy. Why? Because geometry, you have to use these definitions to back up your argument. If I wanted to say, oh, hey, that's a circle, I'd have to prove that from a central point, if I measure the distance anywhere on this circle, it's the same distance, which it's not, so it's not a circle. So that's very important. There's no shortcut to this topic. You have to understand the terms. And that's it. Using a segment's midpoint and endpoint to locate the other endpoint. Here's where definitions come in handy. Midpoint means directly in the middle. So if y is the midpoint of xz and z is on the right hand side of y, x has to be somewhere on the left hand side. Otherwise, y isn't the middle. Like if x was over here, z would be the middle, and if x was right here, x would be the middle. Not that we got that out of the way. The midpoint is smack dab in the middle. That means that the distance from y to z will be the same as the distance from x to y. So we just have to find the distance from y to z. Remember, distance is just the absolute value subtraction. So 14 minus 4 is negative 10, which is just 10. So here to here is 10 spaces. So here to here is 10 spaces. If you know anything about number lines, when you go to the left, you subtract. When you go to the right, you add. Going from y to x, I'm going to the left, so I'm subtracting. So x would be no absolute value here, 4 minus my distance of 10, which would give me negative 6. And that's honestly it for a problem like this. You just have to find the distance between the points they give you, and figure out if your last point is to the left or to the right. If it's to the left, you're subtracting from the midpoint. If it's to the right, you're adding. And that's just it, really. Finding supplementary and complementary angles. I honestly debated whether or not to do this topic because it's so simple, but I'll do it anyway. Ready? Complement is going to be right here. As it says, complement angles just equal 90. Supplement is right here. Supplement angles equal 180. That's literally it for a topic like this. If so long as you remember that a complement equals 90 and a supplement equals 180, you're fine. So if one angle is 59, what's the angle of its complement? You would just do 90 minus 59 and you would get the 31 that it is. Same thing with the supplement. 180 minus 73 and you would get your 107 that would be. So we have 31, 107. If I'm wrong, I'm wrong. It is what it is because math is hard. And that's it, really. Finding patterns in shapes. All you're doing for this topic is exactly what this says. You're assuming that the pattern will go on just as it's shown. So in this case, all I'm doing is making actually, I'm just making this really. Let me actually get my draw tool out. You're just making a sideways triangle. Like one of those pixelated play signs. That's actually what this is gonna just end up becoming. And how do I get to that point? If you look, I'm adding another bar and just taking away the top and the bottom piece. So technically speaking, if you want to get mathy about it, you're just going to do x plus x minus 2 plus x minus 2 minus 2 so on and so forth. That's all you're doing. So if I start it with 1, 2, 3, 4, 5, 6, 7, 8 pieces, this is going to be 8, and this is minus 2, which is 6. So that's 8, 6, minus another 2 is 4. And so my last piece would be 8, 6, 4, and what's 4 minus 2? That's 2. And if I add them all together, 8 and 2 is 10, 6 and 4 is 10, 10 and 10 is 20. So my final figure will have a total of 20 blocks. So you're just recognizing patterns, and that's it for a problem like this. Reflecting a polygon over a vertical or a horizontal line. This is the same exact thing as reflecting a polygon or a point over the y-axis or the x-axis. Except this time you can't just use your cheat code of, oh, if this is 5, then it's going to flip to -5. You're going to have to count points. And that's it. So using my personal cheat code, I'm going straight to the line. And so this is 1, 2, 3, 4, 5, 6 spaces away from my line of reflection. So I'm going to count 1, 2, 3, 4, 5, 6. Place my point. This is 1, 2. So I'm going to go 1, 2. This is 1, 2, 3, 4, 5, 6. So this is 1, 2, 3, 4, 5, 6. Which makes sense because these 2 points are on the same x-coordinate. Oops, I did not finish that. And that's it for a problem like this. Just make sure you keep your counting proper, and you shouldn't have any trouble with any problem in this one. Areas of rectangles with the same perimeter. A rectangular lot is 55 yards wide and 90 yards long. Give the length and width of another rectangular lot that has the same perimeter but a larger area. I'm going to try to condense the math down in this, but I personally find it useful. If you did not know, a square is just a rectangle where the length and the width are equal. So in this case, if this was my square, the length would be, let's just say 2, so the width would also be 2. That's all a square is. A rectangle might look like this, where my lengths are 3, but my width is 1. Note something about this. The area, the inside space, is just length times width. So 2 times 2 is 4. 3 times 1 is 3. So in my poorly drawn rectangular world, this square has a larger area than my rectangle. However, if you do the perimeter, 2 plus 2 plus 2 plus 2 plus 2, 2, 4, 6, 8. 3 plus 1 is 4, plus 3 is 7, plus 1 is 8. The perimeters are equal. How is that? Well, if you notice my length, I just added 1 length to my square and subtracted that same 1 from my width. I kept the ratios even. Basically, if you add any number to your width and subtract it from your length, your area will change, but your shape will still have the same perimeter. Now, with that being said, it makes a problem like this pretty easy. If you want your area smaller, you're going to add to your larger number and subtract that same amount from your smaller number. Basically, you're making your shape into a thinner rectangle. If you want a larger area, you're going to subtract from your larger number and add to your smaller number, making your shape more into a square. The closer these values get to being the same, so let's just say 70 and 70, the larger the area. The closer this gets to 1 and this gets to, let's just say, 150, the smaller. Think about the difference between this rectangle and this rectangle. This can hold way more on the inside, which is what area is, than this can. So pretty much speaking, for problems like this, if they're asking for a larger area, just choose a number. I'm going to choose 5. So for a larger area, I'm going to add 5 to my smaller number, which is my width. So 55 plus 5 is 60. And subtract that same 5 from my 90 and get 85. If I wanted a smaller area, I would do it backwards. Subtract 5 from 55, add 5 to 90. So it really just all boils down to this fact right here. If you want a smaller area, you have to make your bigger number bigger, your smaller number smaller. You're getting it so tiny and so thin, it's almost just a line. And if you want a large area, the largest area you can possibly have is a square. And that's it for a topic like this. Finding a point on a number line given the length of a segment and another point. This is going to be, rectangle. Still on the thing from last topic. This is going to be a pretty straightforward one, but it might get confusing if you don't pay attention. They gave us a point W, which they said is at 3. That's not how you draw number lines. It would be like this. W and 3. Why did I draw it in the middle? Just because. Now, we know the length of WX is 13. But where is X? X could be here, and that's a space of 13. But X could also be here. It's never stated if W or X comes first. So all answers in this topic will have 2 different cases. So remember, if you go to the right, you add. If you go to the left, you subtract. So 3 plus 13, 16. 3 minus 13, negative 10. And those are the 2 different cases for where X could lie. So for a topic like this, you're basically trying to figure out where could X be. It can be either in front or in back. And so if it's in front, you add. If it's in back, you subtract. And that's it for a topic like this. Distance between 2 points in the plane, exact answers. You might notice that I'm still on the explanation screen, but that's because, to be very honest, that's all you really need to know about a problem like this. This is your distance formula. As complex as it looks, all you're doing is plugging in the values of X and Y into this formula. So in this example, my X2, I can call it 2. My X1 is negative 1, so 2 minus negative 1 is positive 3. And the same thing, negative 3 minus 2 is negative 5. 3 squared is 9, negative 5 squared is 25, and 9 plus 25 would actually give us 34. And that's it. You're keeping it as a square root. So I'm going to just do one quick example of this, but it's just a plug and play problem. So if my distance formula is the square root of, subtract your X values. It does not matter the order so long as you keep it in the same order for your Y. So I'm going to start with negative 6. So negative 6 minus negative 1 squared plus your Y's. So I started with negative 6. I'm going to start with 1. 1 minus 9 squared. That's just going to be the square root. Negative 6 minus 1 is plus plus. So that's negative 5 squared plus 1 minus 9 is negative 8 squared. Fun fact, a negative number squared is the same thing as a positive number squared. So negative 5 squared is the same as 5 squared, which is 25 plus 64. which will give me the square root of 89. And that's it. There's no calculator needed here because they do not want the decimal representation. Why? Because your calculator will be rounding what that is. So for example, the square root of 89 in this calculator is 9.4339811320566604. But I can guarantee you, if you put it into a better calculator, you'll get a longer decimal representation. And plus, honestly, that's way too much to be typing out into ALEKs. So just keep it as the square root, assuming you can't reduce it any further. So, for example, the square root of 25 is just 5, and so on. And honestly, that's it for this topic. Midpoint of a line segment in the plane. Find the midpoint M of the line segment joining the points A and B. Finding the midpoint, if you're given both the endpoints, is actually fairly simple. The formula for it is just as follows. The midpoint is equal to the average of your x values and the average of your y values. So in this particular case, I would just do 3 plus 7, which is 10, divided by 2. That's 5. 3 plus negative 5, which is 3 minus 5, is negative 2. Divided by 2 is negative 1. Which looks about right. 5 would be out here. Negative 1 would be right there. That looks about to be my midpoint. So I'm confident in my answer. And that's it for a topic like this. Conditional statements and deductive reasoning. I'm not going to get into every little tiny part of this, but this part will be a little bit long. So let's actually zoom out because we're not going to need nearly as much of this as we do. So if you give a statement in a if-then format, such as if you watch this video, then you may do better. Let me actually write that out. If you watch this video, then you may learn something. When you're given a statement, there are 3 ways, at least currently, there's more than 3, but there's 3 ways in this topic that you can state its truth. So let me underline this. We are going to call P. And this, which I'll change to blue, I guess, is what we're going to call Q. The 3 different statements would be, the first one is P then Q. So if P is true, Q is true. All that means is if I were to tell you, if you watch this video, then you learn something, you may learn something, and you happen to watch the video, then it must also be true that you might have learned something. It's a pretty straightforward, no duh type of true statement. Another case of true is a little bit more different. That is our not Q, then not P. What that means is you make the opposite of your Q statement, then, so it would be just if the opposite of your Q statement, then the opposite of your P statement. So if I were to say, if you watch this video, then you may learn something, this bottom statement would actually read out, if you do not learn something, then you did not watch this video. So it's something that we do say a lot, a few times. For example, if your mom was like, hey, if you clean up your room, then you'll find your phone. And you're like, Mom, I didn't find your phone. Your mom might say, well, you didn't clean your room. It's kind of like that. So that is actually also a true statement, assuming your original statement is true. The last type is with 3 different things, and it kind of sounds like a roundabout. So, if today is Monday, then there is math class. If there is math class, I will see my friend. This one is a little bit redundant, but it's pretty straightforward. So we're going to do P, Q, and R. So we have our, I'm going to just make these all the same color because I'm being lazy now. We have, I poked myself. We have our P, Q, and our R statement. So what this says, if P then Q and Q then R, then you can just take out the middleman. So what this would say is, assuming this is true, then this statement will also be true. If today is Monday, then I will see my friend. All you did was take out the middleman. And those are the 3 type of true statements in this particular topic. So let's see if we can break it down. And I'll show you what to look for in this particular topic. If the tires are old, then Greg knows how to dance. Well, the tires are old, so Greg knows how to dance. It's kind of a straightforward thing. So Greg knows how to dance. If I am my first period class, then Dale heard the radio. There's no extra no-duh statement. So this would be our contrapositive. That's our opposite of the second statement, then opposite of the first statement. So if I am in my first period class, then Dale heard the radio, would be if Dale did not hear the radio, I am not in my first period class. So if Dale did not hear the radio, then I am not in my first period class. Notice how if they give you a statement and then they give you the first part of the statement, your answer will just be the Q, or the second part of the statement. If they just give you one statement, your answer is the opposite of the second part, then the opposite of the first part, which again we call the contrapositive. And the third one is just a redundant one. If geometry is Raphael's favorite subject, then the dress is on sale. If the dress is on sale, then the television is broken. Just take out the middleman. This is what we actually call the transitive property. You're just taking out the middleman. So if this is all true, that just means if geometry is Raphael's favorite subject, then the television is broken. Which obviously doesn't make much sense, but it's not supposed to. It's ALEKs. And so if you can understand implication, which is this, contrapositive, which is this, and transitive, which is this topic is not that difficult. And as a bonus, you'll be a better person in terms of arguments in your real life. Reflecting a polygon across the x-axis or the y-axis. Back to reflecting, translating, or just changing shapes in a coordinate form. There's no shortcut for this. The really only shortcut is, instead of using your pencil for dots, is to keep the dots in your mind and use the lines like I am. Though I guess we did learn one shortcut. If you remember, let me actually get on my draw panel. When we reflect across y-axis, like in, I can't spell, like in this problem, our x changes and our y stays the same. When we reflect across the x-axis, our x stay the same and our y changes. Why would that matter here? Well, to me at least, it makes graphing so much easier. So I don't have to even like count spaces. I know I'm reflecting across the y-axis, so my y will stay the same. I'm going to stay the same height, and my x will flip. If this is -4, I'm at +4. If this is at -7, I'm at +7. -7, +7, same height. And if this is at -8, I'm at +8. So it makes, for me at least, graphing so much easier when you remember those tricks, so long as you read the right axis. I messed up at least 3 different times getting to this point because I kept doing the wrong axis. But outside of that, that's all you really need to do a problem like this. Computing distances between decimals on a number line. This isn't exactly a hard topic, it's just dealing with decimal numbers, doing the same things we've been doing. So BA is the distance, oops, that's my text box, is the distance from this to this. So we would just do the absolute value of -5 minus 3.5. Now, I'm going to just be honest with you, especially if you're going from a negative number to a positive number. If you're not comfortable doing this whole absolute value thing, just count it. -5 to 0 is 5 spaces. 0 to 3.5 is 3.5. 5 plus 3.5 is just 8.5. Oops, 8.5. And if you're dealing with 2 positive numbers or 2 negative numbers, you just subtract the bigger one from the smaller one. 16.9 minus 3.5. 9 minus 5 is 4. 6 minus 3 is 3. 1 minus 0 is 1. So that would just be 13.4. So the absolute value way is very useful, especially if you don't just have a number line in front of you. But if you have a number line, feel free to use whatever trick you have up your sleeve. The main point is, can you do this without a calculator? Because anybody could do this with a calculator. That's what calculators are for. But doing this without a calculator, make sure that if your calculator is dead, your phone is dead, or if you're doing this on a job that doesn't allow electronics, which a lot of jobs actually don't, you know what you're doing. It's the difference between I know how to do this and I don't know how to do this, but my calculator does. And that's it for a topic like that. Solving an equation involving complementary or supplementary angles. Remember, complementary just means they equal 90. Supplementary means they equal 180. Complementary is this right angle here. Supplementary is just a straight line. So we know these two are complementary because it's not a straight line and it's just right angle. That box is complementary. So we know that angle 1 plus angle 2 equals 90. One equation down, one more to go. Just so you know, this is going to be like a substitution or an elimination problem, but way easier. So we know that angle 1 is just x plus 42. Angle 2 is 3x. So now we solve for x and plug it into our equation. X plus 3x, I know that looks like times, but it's plus. X plus 3x is 4x, plus 42 equals 90. Subtract 42 on both sides. 4x equals 48, divide by 4. And x equals 12. Now that we know what x equals, we just plug that into our angle 1 and our angle 2. I'm just going to do the math mentally because I'm fancy. 12 plus 42 is going to give us 54. 12 times 3 is 36. Assuming I did my math right, that should be it for a problem like this. Again, it's just, if you understand that complementary is equal to 90, supplementary is equal to 180, and you know how to set up your equations, these problems won't give you any problem at all. Angle addition with relationships between angles. Angle, let me actually get this right up. Angle ABD, which is this entire thing, is 100. What is angle ABD made up of? Well, angle 1 and angle 2. So we know that angle 1 plus angle 2 equals 100. I'm going to call angle 1 x and angle 2 y to make life simpler. X plus y equals 100. Angle 1 is 4 times angle 2. Now we're just back to goal 5 at algebra 1 with substitution and elimination. If x equals 4y, we just plug this into our equation, and we get x plus y equals 100. 5y equals 100. Y equals 20. Now, don't be so quick to put that back into your answer because it's not asking for angle. Oh, it is. Never mind. I lied. Ignore me. I'm tired. Yes. Y is 20. And what is y? That's angle 2. I was going to say make sure you plug it into your equation, but we don't need to for this. I almost got confused with my x and y. That's why it's good to have this written down so that when you find y or x, you're like, oh, that's going to be the angle I was looking for. So yeah, that's it for a problem like this. And if I'm not mistaken, and I always tend to be, because I am human after all, this should be the end of our goal. Is it? Ah, yes. And that is the end of goal 1. Now, there is more topics on goal 1. If you haven't noticed by now, ALEKs will only make you do 80% of the total topics in a goal, which means that if you're skipping around, there are some topics that you probably were trying that I didn't go over. So for example, and it's taking so long to load because I'm recording at the same time and my computer, as good as it is, kind of doesn't like that. If you go to your Learn station and it loads after, 20 years because you're recording a 2-hour and 35-minute video and your computer's kind of freaking out because it's a lot of video. If you go here, if I go down to goal 1, I completed 80% of it, which means that these are still topics that would probably be useful to learn. Like, as you can see, I actually started some topics that I didn't do. I didn't have to do. And I'm not going to make videos on these unless you ask me to, because laziness and tiredness. I've been at this for like 2.5 hours and it's 9:30. But I didn't do like 12 topics. So you can skip around if you didn't feel comfortable doing the topics that I did. But generally speaking, that's it for goal 1. Tune in next time for goal 2. And let me know how you like this video format. If you just like the one giant video with different splits in it for your topics, let me know. Otherwise, I'll try and go back to the shorter videos with only one topic in it. The difference being, this video will be way easier for me to just edit as one versus splitting it into multiple tiny videos. So let me know what you think about it, and hopefully you did in fact learn something from this. Other than that, I wish you luck, and until next time.